Okay, in this problem, we're going to work on a Wheatstone bridge and a differential op amp. So this part of the circuit is the Wheatstone bridge. And this part is the differential op amp. Okay, and one thing to notice about the Wheatstone bridge, it looks tough because it looks like a diamond of resistors. But if you think about it, there's a voltage source here, and it's connected to each side of this set of resistors. So we actually have like a branch that goes, here to ground. So you can see this goes from the voltage source. So say this is, in our case, it's 10 volts. So we have 10 volts that we're dropping across R and RV to 0. And then for our other side, we have the same thing. So we have this voltage, 10 volts, and we drop it across this resistor and across this resistor to ground. So really what we have is just two voltage dividers. So if we were to redraw this, we would draw this. So this is the left side where we have R and RV, 10 volts. And then on the right side, we have 10 volts, and we have R and R. That's really all that's happening in this diamond of resistors. We just have two voltage dividers. And this is our VA, and this is our VB. And if you notice, because this R and this R are the same, we're really just, our VB, right? The VB value is just going to be equal to 5 volts. Just 10 volts divided by 2, because we're splitting it equally across those two resistors. Now on the left side, what we're going to have this for VA, just move down a little bit, we're going to have VA, we're going to use the voltage divider equation, and we're going to say 10 volts, the voltage, the supply voltage, times R2, which in our case is RV, the bottom one, divided by R plus RV. And if we work that out, we're going to, in our case, I'll show you our givens. So our givens are V in is 10K, RF and RI are 2K, 8K and 2K respectively, and then RV is 402 and R is 350. So over here, we're going to have 402 divided by 350 plus 402, all times 10K, or 10 volts, sorry. And so VA then is equal to 5.37, just erase that, 37 volts. And that makes sense because if my RV is, if this RV here is 402 and our R is 350, then we would expect to have more voltage, more than 5 volts left for RV because that resistor is bigger. So that makes sense. So now we have, so that gives us our values for up here. So we now know this VA is equal to 5.37 and this VB is equal to 5 volts. So looking over here, so my voltage here, this VB is 5 volts, and my voltage here, right, goes back to, it connects back to over to here to VA, and so that value is 5.37. Right, so now we can treat this just like a differential op amp. So remember, in that case, for a differential op amp, we can look at the general equation for differential op amp, and that is that V out is equal to RF over RI times V A, right? Because that is VA is connected to the positive minus VB. And if we plug in, we get 8K divided by 2K times 5.37 volts minus 5 volts. And multiplying that through, we get V out is equal to, let's see, 1.48 volts. So what we want to do now is we want to go through the steps and figure out what our voltage drops are across our, this is, just fix this a little bit. This is volts, and then I have these marked wrong, so let me just erase. This RF should be RI. Okay. All right, so now I have, I'm going to start, where I'm going to start is right here at VA, when VA goes into the positive input. So, let's see, I'm going to start, let's change the color a bit. So I'm going to start right here at 5.37. So what I want to do then is I want to, if VA at this point is 5.37, then I can calculate the voltage drop across here, right? And that allows me to find both the current in those resistors, but also the value of V plus right here, so that I can set it equal to V minus right here. So let's go ahead and do that. Okay. So I'm going to say, I'm going to call this for the bottom, meaning the bottom set here, or let's say it's the plus side of the op amp. So I want to know what the current is. So I'm going to say I plus is equal to VA minus 0, because that's the voltage drop, across RI plus RF. So that's going to equal 5.37 divided by 2K plus 8K. And that gives us 0.537 volts, or so, amps, milliamps. And now I can calculate, so now that I have the current, I can calculate the voltage right here if I find the voltage drop across here. And I can just use my I plus here times RF, and that'll give me the voltage at that spot at V plus. So V plus is equal to I plus times RF, and that's equal to 0.537 milliamps times 8K, and that's equal to 4.3 volts. So I have 4.3 volts right here. So that means I have 4.3 volts right here. And now I can also figure out my V across RI on the bottom. And that's going to equal VA minus V plus. And that's equal to 5.37 volts minus 4.3 volts, or 1.07 volts. Okay. And I already have my voltage, so this right here is also equal to my VRF on the bottom. Okay, so now that I have this 4.3 right here, I can calculate my voltage drop across RI here, and then also my current through RI. And that current will be the same as the current through RF. Okay, so I also can notice that because the voltage at VB is greater than the voltage at V minus, my current is going to go this way. So this is going to be my I minus. In this case, I had over here, this was my I plus. It also traveled that way, but this is going to be my I minus is going this way. Clear this out just a little bit. So this is 5 volts. This current goes this way, and that's going to be I minus. There we go. Okay, so now we're going to go to the top. Say that's on the negative input to the op amp. So first we're going to say V of Ri is going to equal V of B minus V minus which is equal to 5 volts minus 4.3 volts, which is 0.7 volts. So now I can figure out I minus is going to equal V Ri divided by Ri. So that's equal to 0.7 volts divided by 2K, or 0.35 milliamps. And now I have, since I have I can calculate my voltage drop across RF to get V out. So the way I'm going to do that is I'm going to say 4.3 volts here minus the voltage drop across RF, which is I times RF, and that'll give me V out. So let's go ahead and do that. So first we're going to say V of RF is going to equal I minus times RF. That's equal to 0.35 milliamps times 8K, and that's equal to, 2.8 volts. And so now V out is going to equal V minus plus, is that right, plus? No, it's minus. Minus VRF. So that's going to equal 4.3 minus 2.8 volts. And that will equal 1.48 volts. And if we check back, that is the same thing we got over here. So that looks like we're doing it right, both with the formula that we can use here, or with starting from using currents and voltage drops, starting over here from the Wheatstone bridge. So I think that we have everything, and that's it. One thing I guess we can talk about just for a minute is if we know on a Wheatstone bridge feeding into a differential op amp, this V out, this is just kind of a side note, this V out provides information about this resistor here. And usually this resistor, this variable resistor, is a sensor that has a certain resistance, and that resistance is correlated with the thing you're measuring. So it could be temperature, it could be light level, it could be pressure level, whatever your sensor is. That resistance that your sensor is detecting, right, is determined by, can be calculated by this V out. So the V out provides information about that. And so what you can do with a circuit like this is you can feed this into another circuit that controls something about the environment that would change the value of your RV. So I can say, for if I were trying to control the temperature, I could use this V out as input to something that heats something up, so that I could increase the temperature. Or maybe you have something that where you could decrease the temperature, like turn on a fan, and that would decrease the temperature. And so you could use this signal, that V out, to control for another device that controls that RV, and we can have like a controller to be able to control the temperature, because we're measuring the temperature and we're feeding that into something that changes the environment, that changes the temperature, that changes the resistance. So we can have this feedback circuit that automatically is controlling something about the environment that causes this resistance to change. And we can set it by having the right relationship between our resistors here. So we can drive this circuit with V out to be able to try to match VA to VB, or if we were, say, looking for a certain light level or a certain temperature. So that's one way that we can go about using a Wheatstone bridge and a differential op amp circuit.